In this formal lab, we designed an experiment in order to test how the different variables affect the energy of the system of a ball when it bounces off of a surface. Testing how the height of the ball affects the energy of the system when it bounces off of a surface helps indicate how the kinetic energy of the system changes as a result of the differences in the height.
The experimental design of our experiment is laid out here on this slide. We wanted to see how the initial height of the ball impacts the kinetic energy in the system. So we chose 4 different heights and we recorded 3 trials for each of them. Down here is an example of us analyzing a trial on tracker, and down here on the right bottom of the screen is a system schema of our experiment, which includes the ball and the earth with gravity between them. The person is not included in our system schema.
Qualitative conclusions, we found that the maximum gravitational potential energy is at the dropping point. This is because the height is the greatest here. Gravitational potential energy decreases as the ball falls because the height is decreasing. The ball's kinetic energy increases as the ball falls because the velocity is increasing. Because of this increase-decrease relationship, the overall energy is conserved. When the ball bounces, the energy is not conserved because it dissipates due to friction from when the ball touches the ground as well as air resistance. This is why the ball comes to a stop after bouncing. For the energy pie charts at 100 centimeters, there is 100% gravitational potential energy before the drop. Halfway to the floor, there is 50% kinetic energy because the ball is increasing in velocity. Right before it hits the floor, velocity is at a maximum, which is why kinetic energy makes up most of the pie chart. At 100 centimeters, there is 0.909 joules of gravitational potential energy. Because energy is conserved, this is the same amount of energy as the point of maximum kinetic energy. We can solve for the velocity at this point, and it is consistent with the tracker results.
The next height we dropped the ball from was 75 centimeters. Here are the energy pie charts for this drop. They are the same as for the 100 centimeter drop, besides the fact that the radii are smaller due to there being less total energy. There's only potential gravitational energy before the ball was dropped, and halfway through there was an equal amount of gravitational and kinetic energy, and just before the ball hits the ground there was a majority of kinetic energy. The gravitational potential energy at 75 centimeters was 0.682 joules, and the kinetic energy just before the ball hit the ground was 0.682 joules as well. This shows how energy is conserved in the system. The velocity was negative 3.83 meters per second. Here are the energy pie charts for the 50 centimeter drop. Again, they are the same besides the fact that the radii of the circles are smaller due to there being less total energy. The gravitational potential energy was 0.455 joules, and the kinetic energy just before the ball hit the ground was also 0.455 joules, again showing how the energy is conserved in the system. The velocity is negative 3.13 meters per second. The last height we dropped the ball from was 25 centimeters. Again, the energy pie charts are the same, besides the fact the radii are even smaller than the 50 centimeter drop due to there being less total energy in the 25 centimeter drop. The gravitational potential energy for 25 was 0.227 joules, and the kinetic energy before the ball hits the ground was 0.22 joules as well. Once again, showing how energy is conserved in the system. The velocity was negative 0.21 meters per second. The velocity calculated and the velocity found on the graph does not match, so there must have been some error in the trial to cause these values to be different.
As with any experiment, you are bound to come in contact with error. Some ways we reduce this was by having the same person hold the meter stick and the ball in the same positions. We weren't able to eliminate random error, however, which includes the determination of the ground on tracker and the exact height of the ball each time. The quantitative errors were represented by the standard deviation, which is a numerical value representing the extent of deviation among a set of values. The equation for that is down here on the bottom of the screen. Here on the right is the deviation or the standard deviation for each point regarding kinetic energy. In comparison with the kinetic energy values we had, this is quite a large margin of error. However, this is due to the fact mostly of the random error that we were not able to eliminate.